Nag-start na po.
Hindi, baka nag-share lang.
Wait lang po, wait lang.
Okay na, sir. All right, good afternoon. I hope everyone's got their energy back since we all took our lunch. Now, for this afternoon, we need a lot of energy since we still have 5 more topics, no, from our speakers and lots of knowledge to acquire.
Before we move on to our next speaker, let us hear a video recorded message from one of our collaborator, the head of the University of Science and Nueva Ecija University of Science and Technology, Dr. Aurora R. Hugo.
Dr. Renato G. Reyes, President of Aurora State College of Technology, Dr. Maria Luz F. Cabatan, VP for Academic Affairs, Dr. Oscar C. Barawi Jr., VP for Administration, Planning and Finance, Mr. Joseph Gonzalez, International Affairs, External and Alumni Affairs. To my fellow presidents from various state universities and colleges across the country, the faculty and students of ASCOT, as well as other participants, a pleasant day to all. Innovation knows no limits, and engineering continues to be a driving force in addressing some of the world's most pressing challenges. As we navigate an era of rapid technological change, the need for cross-border cooperation has never been more important. It is a privilege from the Nueva Ecija University of Science and Technology to collaborate with Aurora State College of Technology through this webinar that provides a unique opportunity to exchange knowledge, inspire one another, and build partnerships that transcend geographical borders. Today's discussions and presentations are the seeds of future collaborations and transformative ideas. Therefore, I encourage everyone to use this platform to learn not only about technical advancements, but also about how we can work together with a shared vision for progress. Congratulations to Aurora State College of Technology for this initiative. Wishing everyone a productive and meaningful experience ahead. Mabuhay tayong lahat. God bless us all.
Thank you, Ma'am Hugo. Now, let's move on to our sixth speaker. So, our sixth speaker is Dr. Kiran Prakash Shinde. He is a researcher professor of Sejong University, Republic of Korea. He will be presenting on the topic Magnetic Refrigeration, the future of eco-friendly cooling technology. Let's give him a round of applause. So we can see his research experience. His patents. Again, let's give him a round of applause.
Thank you.
Hello, Dr. Shinde.
Yes. Hello, I'm audible?
Yes, sir.
Yeah.
Loud and clear.
Okay, good. Good afternoon to all the participants. First of all, I would like to thank the organizers for giving me opportunity to talk in this international webinar. I am Dr. Kiran Shinde from Sejong University, South Korea. Today I will talk about the new technology like magnetic refrigerant can help us to cool the things without the harming environment. And topic of my presentation is magnetic refrigeration, the future of eco-friendly cooling technology. My presentation consists of the introduction to the current cooling technology. Then I will talk about the magnetic refrigeration and its basic principle, which is nothing but the magnetocaloric effect. Then I will talk about the magnetocaloric material, which is nothing but a double perovskite structured material. And then I will talk about some results based on this rare earth based double perovskite material, and I will end with my presentation with some conclusion. And so friends, our society is highly reliable to the refrigeration. So here we can see that the food storage or food transportation, like dairy products or fruits and vegetables, they are cultivated to the countryside and they have to transport from to the rural to the urban area. So these are non-perishable, so we need cooling for this kind of dairy products or fruits or vegetables, so we need a cooling. Again, because of global warming, we need a cooling into the transportation, like trains, buses, aeroplane, and even in shopping malls and in hospitals, especially for cryosurgery. Then we can store the organs at a low temperature, and we can use that for the transplantation to the other patients. These are the room temperature application, and at the middle here I show that the liquid hydrogen storage. Nowadays we are using the hydrogen based vehicles, and you know hydrogen is inflammable gas. So the big problem with this hydrogen is flammable. So we have to handle it with very highly precautions. So we have to use this high compressor to get it liquefied, and we can store into this compressed chambers. So transportation and liquefaction, it need high energy. So this kind of technology, for this kind of cooling, so we need high energy. So the technology which we are using for this kind of refrigeration is not cost effective, it's highly expensive and not energy efficient. Then another parameter is we have to think about the gases which are coming out from this refrigeration technology, which is like we can say the vapor compression refrigeration. They use greenhouses like CFC, chlorofluorocarbon, and that emit some gases to the environment, and that can cause the global warming because it affects to the ozone layer. So we have to find the new technology which is highly energy efficient and eco-friendly, and which is nothing but the magnetic refrigeration. In this slide we can see that the magnetic refrigeration cycle. Magnetic refrigeration is nothing but the heating and cooling with the application and removal of the external magnetic field. Here we can see that when a ferromagnetic material or magnetocaloric material, when placed into the external magnetic field, which carrying the magnetic dipole, when they are in the external magnetic field, they try to align to in the direction of a magnetic field. So when they align, the magnetic entropy of the material is reduced. As we know, under the adiabatic condition, the total entropy of the material or system, we can say that is a constant. Then the reduced part of magnetic entropy is transferred to the lattice by lattice pin coupling. So because of that, atoms into that material get vibrated, and we can get the heating effect, and temperature of the material is increased. Then when we remove the external magnetic field, then these parallelly aligned magnetic dipole moment, they try to reorient to their original position, and we can get the cooling effect. In this case, when we apply the magnetic field, then temperature is increased. When we take it out, that heat using the coolant, then we can get the heat can be extracted from the system to the environment. And when we remove the external magnetic field, at that time, heat is absorbed from the system by that material, magnetocaloric material, and we can get the cooling effect. This is nothing but the magnetic refrigeration cycle. So the magnetic refrigeration is working on basic principle, which is nothing but the magnetocaloric effect. Here, this slide shows how magnetic caloric effect actually works. When ferromagnet is placed to that magnetocaloric material, then randomly oriented dipole moment, they get aligned, and temperature is increased, and it is expelled out to the environment. And when we remove the external magnetic field, then they try to reorient to their original position. During this time, we can get the cooling effect, and temperature of the system is lowered down come to its original temperature. So it is nothing but the change in the temperature with the application and a removal of the magnetic field. So this slide shows the comparison between the present vapor compression refrigeration cycle, which is we are using for all the cooling appliances, and the new technology, which is like magnetic refrigeration, and which is shown in the cycle form. So the application and removal of the magnetic field in this magnetic refrigeration, which is analogous to the compression and expansion of the vapor compression refrigeration. So here, when we apply the magnetic field, we get the heating effect. Similarly, when we compress the gas in vapor compression, we get the temperature is increased. But when we remove the external magnetic field, we get when we remove the external magnetic field, then heat is absorbed by the system, and we get the cooling effect. Similarly, like expansion valve in vapor refrigeration cycle. So this slide shows the advantages of this magnetic refrigerator over the current refrigeration technology. As we see that in vapor compression refrigeration, we use the gases and compressor. So there is a noise, and in case of the magnetic refrigerator, we don't use any kind of compressor. So that kind of technology is noiseless, we can say. And another thing is like its efficiency of the vapor compression is up to the 30% of the Carnot efficiency, while in case of the magnetic refrigeration, we can reach up to the 75% of the Carnot efficiency. So economically also, we can say that this magnetic refrigeration technology is energy efficient, and it can be used for the various applications such as gas liquefaction, as I said, in hydrogen liquefaction or hydrogen storage, hydrogen transportation, then room temperature cooling application, then electronics, space industry, and medical industry also. So here we can see that how we can prepare the magnetocaloric material by physical and chemical methods. In chemical methods, we can use different sol-gel methods, then hydrothermal method, and we can also prepare the nanoparticles. So we can check the effect of the nanoparticles on the magnetocaloric properties. So after the fabrication of the magnetic material or magnetocaloric material, we have to use the magnetic property measurement systems, MPMS, or physical property measurement system. Using that equipment, we can measure the Curie temperature of the material. Then we have to measure the MH around TC, like before and after TC, and we have to use this theoretical equation to analyze the magnetocaloric material. So in this slide, I'm going to talk about the magnetic moment with respect to temperature. We have to use this kind of measurements for the determination of the Curie temperature. When we take the differentiation of this magnetic movement with respect to temperature, we can get the Curie temperature. In this slide, I am showing the Curie temperature for the gadolinium material, which is 299 Kelvin. So gadolinium is the one of the best material to use in room temperature cooling application, and it is showing a higher magnetic or magnetocaloric property around the 299 Kelvin. So as I said, this equation we have to use for the measurement of magnetocaloric property, delta Sm. So the magnetic entropy change is maximum around the Curie temperature. So magnetic entropy change is maximum around this temperature, or we can say that in this temperature range, we can use this gadolinium film for the application purpose. So delta T or change in temperature in this gadolinium case, it's 2 Kelvin per Tesla. So if we use the 5 Tesla magnetic field, we can get 10 Kelvin change in temperature. So 10 Kelvin is good enough to cool the room temperature for the application purpose. So in this case, maximum entropy change is observed is equal to 9.8 joule per kilogram per Kelvin when we apply the 5 Tesla external magnetic field. This slide shows the various magnetocaloric material from the discovery of this magnetocaloric effect. In the 1976, Professor Brown, he achieved the magnetocaloric effect in gadolinium first time at room temperature. After that, in 1997, Pekarskaya and Justinder from Iowa State laboratory from United States, they developed this gadolinium germanium silicon based intermetallics magnetocaloric material, and they found a giant magnetocaloric effect in this particular system. Then after that, in 1998, the first device or prototype was developed into the United States, and after that, so we can see that manganese arsenic based intermetallics, then iron based intermetallics, then rare earth nitride was developed first time in Japan in 2004. And these rare earth nitrides or rare earth oxide, they can be useful at cryogenic temperature region, like as I said, liquefaction of hydrogen, as hydrogen is getting into the liquid state at 20 Kelvin. So this kind of rare earth nitrides and oxide, they are showing the magnetocaloric effect around 20 Kelvin. So they were discovered in 2004. After that, manganites were developed, first time reported by Professor Fan, who is currently working in United States, and he also he worked in Korea during his masters. So he studied many series in the manganite MC material. Then double perovskite. Recently, many people are working on this kind of material, and high entropy alloy. Also, in 2020, many people started working on the high entropy alloy for this magnetic radiation. So here we can see that or magnetic caloric material with respect to their Curie temperature and respective magnetic entropy change when we apply the magnetic field 5 Tesla. So these material, they are divided into two groups, like first order phase transition and second order phase transition material. So first order phase transition material, like having some drawbacks when we are using this kind of material for the application purpose. Even though they have high magnetic magnetic entropy change, but the working temperature is smaller when we compare to the second order phase transition material. Then another drawback with this first order magnetic transition material is they are having the magnetic hysteresis loss. So when we use this material for application purpose, these are not feasible. But when we use the second order phase transition material, we can get the reversible magnetic entropy change curve. So when we study this kind of material, then first we have to check these are first order or second order phase transition material, and how we can determine they are first order or second order phase transition material. Using this Aurora plot, which is nothing but the square of magnetization, and when we plot it against with the magnetic field with divided by magnetic moment, and we can get this kind of graph which is called as Aurora plots. And for first order phase transition material, we can see that the slope of these different plots, Aurora plots at different temperature, we can see that positive slopes and negative slopes. When they have positive slopes, we can say they are first order, second order transition material. But first order, we can see that there is a negative slope, so they are confirmed that they are having the first order phase transition material. Here we can see that on the right hand side, all the Aurora plots at different temperature, they are showing the positive slopes. So we confirm that the material is second order phase transition material. So we have to confirm first before the going further for detailed study in this kind of materials. So here I am talking about the one double perovskite structural AMC material which I studied. First, let's see about what is perovskite structure. Perovskite structure is nothing but the AbO3 type crystal structure or calcium titanite structure. Here, A side cations are alkali metals like lanthanum, calcium, strontium, and B side cations are transition metal based ions, cations like iron or manganese, etc. Then when we double this structure, like the cation and anion in this perovskite structure, like A2, B prime, O6, which is called as a double perovskite structure. Here we use the gadolinium, nickel, and manganese at the B prime side, and nickel at the A side, B side of the crystal structure. So for our study, we use the different rare earth element like terbium, gadolinium, and europium, and we studied the crystal structure, the magnetic and magnetocaloric property of this double perovskite structure, and we just try to play with this A side crystal structure of this double perovskite material, and we just replace the europium, gadolinium, and terbium, and we check the effect on the magnetic and magnetocaloric property. So here we can see that X-ray diffraction pattern of these three different double perovskite compound, and its crystal structure is monoclinic with space group P21/N, and these results were published in scientific report in 2021. So as we know, the manganese having the different valence, so we confirm that using the X-ray photoelectron spectroscopy, what kind of magnetic state of the manganese element is present into these different studied compounds. So we found that there is a variation of the manganese 3 and manganese 4+. So we check the ratio and we check how it affect onto the magnetic property of the double perovskite material. In this slide, we can see that the magnetic movement with respect to temperature MT curve, which we use for the determination of the Curie temperature. So here we can see that for europium, gadolinium, and terbium based on three compounds, we measure the magnetic movement and we take the differentiation of this magnetic movement with respect to temperature. Then here we can see that plot, we can get the minimum into this dm by dt curve, which is nothing but the Curie temperature. So when we change the europium, gadolinium, and terbium, three different rare earth elements to the A site of the double perovskite, then we found that the Curie temperature is changing from 143 Kelvin to 112 Kelvin. So actually, when we are using this kind of material for the application purpose, we have to focus on the working temperature. Like if we want to use this material for room temperature application, then room temperature is 300 Kelvin. Then we have to find out or tune the Curie temperature of the material to the room temperature. If we are working at the cryogenic temperature region like 20 Kelvin, then we have to tune the Curie temperature or find the new material having the Curie temperature particularly at that working temperature. So we are trying to just check the effect of the different A-site element into the double perovskite and how it affects on the magnetic property, MC property, and how we can tune the Curie temperature. So if we change this A-site element, then we found there is a drastic change in the Curie temperature. And here we can see that the inverse susceptibility with respect to temperature, and we determine the total effective magnetic moment of the particular material. Then to determine the magnetic entropy change, we have to measure the MH plot, like this magnetic moment with respect to magnetic field at different temperatures. So we determine the magnetic this Curie temperature for particular compound, 143 Kelvin, 130 Kelvin, and 112 Kelvin. So to determine the magnetic entropy change, we have to measure this MH plot at the temperatures. So we have on the right hand side of this slide, we can see the Aurora plots for these three different compounds. So the slopes for these Aurora plots all are positive. So we confirm that this prepared material are showing the second order phase transition material, so which can be useful for the practical applications. So in this slide, we can see that the magnetic entropy change for this studied compound, which is denoted as delta SM joule per kilogram Kelvin on the y-axis, and on x-axis we can see that temperature. So we calculate this magnetic entropy change values using this formula. Delta SM is equal to integration over 0 to h dou m by dou h into dh. Using this formula, we determine the delta SM value and plot it with respect to temperature. And here we can see that the magnetic entropy change delta SM is maximum around the Curie temperature of the particular compound. Because at the Curie temperature there is a maximum amount of the magnetic dipole moment, they are parallelly aligned to the external magnet. When going on the this material can be used for the temperature range in between 100 to 140 Kelvin for the cooling application. But that is not our target. Our target is to develop or find out the MC material that can be useful for the room temperature cooling applications. So we have to find out the particular compound that can show the Curie temperature around room temperature and its MC value higher. So in this studied compound, we can see that Curie temperature is changing from 143 Kelvin to 112 Kelvin when we apply the 5 Tesla external magnetic field. But there is not significant change due to the delta SM value. And again, another parameter we have to determine, that is relative cooling power, RCP is equal to minus delta SM into delta T FWHM. We have to use this formula to determine the relative cooling or cooling efficiency of the particular material. Here we can say there is a change in the cooling efficiency, but important thing is we got the change in the Curie temperature, or we can tune the Curie temperature when we play with the A side. Similarly, when we study the B side element like nickel, instead of nickel, if we replace the nickel with the different transition metal, we can get the change into the Curie temperature. So we have to tune the Curie temperature regarding to our application purpose. So this slide again showing the delta SM with respect to the external magnetic field. We use the 0 to 5 Tesla magnetic field, and when we feed this data using this equation, then we can get this N value for 3 different compound, 0.73, 0.73 and 0.75, which is nearly equal to the mean field theory value of N is 0.67. So which confirms that our studied compound is showing the second order phase transition material. So here are some conclusion of this double perovskite materials. Using the solid state reaction, we developed this rare earth-based double perovskite, and we found that change in the Curie temperature from 112 Kelvin to 143 Kelvin when we replaced A side element. Then we confirmed that this compound showing the second order phase transition present in this material, and we found that the magnetic entropy change is 3.3, 3.8 and 3.0, which are nearly equal, but we found nearly equal the magnetic entropy change into this material, but Curie temperature we see the drastic change into the materials. So similarly, when we dope the A side, we can play with the B side of the material, this kind of a double perovskite material, and we can tune the magnetic property or magnetocaloric property as per our target temperature for the cooling applications. So as far as we know, the traditional system releases the harmful gases which damage the environment and causes the global warming. So we have to go for the new technology, which is nothing but the magnetic refrigeration. But magnetic refrigeration we cannot use for the room temperature application currently, because it is the material which are available or which showing the good magnetocaloric effect needed high magnetic field up to 5 Tesla. But many research groups and all over the world, they are working on the various magnetocaloric material to improve the cooling efficiency and develop this cooling technology. So particularly in this research area, we are finding the new material or magnetocaloric material that can show the higher magnetic caloric property with the lower magnetic field, so that we can use this technology for household applications and as well as cryogenic temperature region like hydrogen storage and hydrogen liquefaction. So to develop this technology as a greener or cooler future of the planet, material scientists and engineers have to come up and work on this magnetic refrigeration technology to come up and use this technology for the practical application for the humans life. Thank you.
Thank you so much, Dr. Shinde. Now, let's accommodate some questions
Sure.
from the participants here. Yes. Please stand. Microphone, please.
Hello.
Hello.
Good afternoon, Doctor. I am Von Vincent Bermudo, a mechanical engineering student of ASCOT. From what I understand, refrigerants are still present in the system. Magnetic system replaced the compressor. My question is, what is the refrigerant used for the system?
Refrigerant. Currently or in magnetic refrigeration you are asking? In vapor compression, we are using the gases. But in magnetic refrigeration, we are going to replace these gases with the magnetic material, which is solid material, so which are not evolving any greenhouse gases.
Okay.
So the magnetic material will be replace the gases into the vapor compression refrigeration. So if we remember the comparison between the vapor compression refrigeration cycle and magnetic refrigeration cycle, so gases are replaced with the magnetic material in this new technology.
Okay, doctor. Thank you.
Thank you.
Thank you so much. So is there any question? Yes, there is.
Good afternoon, everyone. My name is Mary Grace Serbadulia from BS Mechanical Engineering. My question is, how could magnetic refrigeration revolutionize energy efficiency in cooling system while reducing environmental impact?
Okay, nice. Thanks for nice question. As we know, the vapor compression using the different gases like the CFC and SCFC, they are evolving into the environment. So, which affecting to the ozone layer of the environment, and because of that, it affect to the global warming. Another thing in the vapor compression is the efficiency is not higher. So it is until now this technology reaches to its maximum efficiency, but which is like 30% of the Carnot efficiency or Carnot engine, we can say. But if we compare to the magnetic refrigeration, the efficiency we can go up to the 70% of the Carnot engine, which is double to the present cooling technology. So the drawback with this current magnetocaloric material is that they are showing this magnetic entropy change or this magnetocaloric effect.
So we have some connection issue, internet problem here. So may I request everyone who's connected. Sa kanila ba? Hello, Dr. Shinde. So, you're disconnected.
Hello?
Yes.
Yeah, I'm here. It was disconnected. Any more question?
Yes, can you repeat the question? Yes, there is another question.
Yes, please.
Good afternoon. I am Joanna
Good afternoon.
Macalino from BS Mechanical Engineering program. And my question is, what kind of magnetic system did you use in your study? Permanent magnet like neodymium or electromagnet? And how does superconducting magnet affect the efficiency of this refrigeration cycle? Thank you.
Actually, the material which are developed until now in different laboratory, they are tested with the superconducting magnet because they are showing this magnetocaloric property with the higher magnetic field. So using the permanent magnet, until now nobody succeed to get this magnetocaloric effect, because with the permanent magnet we can generate the 1.5 Tesla magnetic field, but that is not enough currently. So research is going on to find out the material or tune the magnetocaloric property with lower magnetic field, we can get the maximum magnetocaloric effect. So nobody tested with the permanent magnet. So all the prototypes, there are 5 to 6 prototypes in the world. They tested with the superconducting magnet.
Thank you po.
Yes, there is no other question. Now let's move on to the awarding of the certificate for Dr. Shinde. Let me read first the content of the certificate. Republic of the Philippines, Aurora State College of Technology, Barangay Zabali, 3200, Baler, Aurora, Philippines. This certificate of appreciation is given to Dr. Kiran Prakash Shinde for your dedicated participation as guest speaker in cross-border engineering innovation at Aurora State College of Technology, ASCOT Hostel, Barangay Zabali, Baler, Aurora on April 29, 2025. Given this 29th day of April 2025, signed Engineer Alking B. Gorospe, PhD, Director, Research and Development Office. Signed Malus F. Cabatan, PhD, Vice President for Academic Affairs. Signed Renato G. Reyes, PhD, SUC President 2. Let's give him a round of applause. Again, thank you so much, Dr. Shinde.
Thank you.
All right, now moving on to our next speaker. Another trivia. Our next speaker is a former faculty of the School of Engineering in the Mechanical Engineering program. Because our seventh speaker is Engineer Richard Gonzalez Pascua, a PhD student, research assistant at Gyeongguk National University, Republic of Korea. Engineer Pascua will present his topic titled Evaluation of Materials under Hydrogen Environment Using Small Punch Testing Method. All right, flashing the background of our next speaker, Engineer Pascua. Okay, so many publications and research contributions. All right. Engineer Pascua, the floor is yours.
Good afternoon.
Hello, Sir
Can you hear me?
Richard.
Can you hear me?
Yes, we can hear you from here.
Okay, good afternoon to everyone, to my fellow ASCOTians, and to all faculty and staff at ASCOT, and especially to engineering family. Good afternoon. And I'm Engineer Richard G. Pascua from Gyeongguk National University, and currently taking a PhD degree with the major of Mechanical Design and System Engineering in the said university. And today, I'm going to present to you our current study in our laboratory, which is the evaluation of material behavior in hydrogen environment using the small punch testing method. So here are the contents of my presentation, which is divided into 5 sections, from introduction, objective of study, methodology, results in discussion, and lastly, the summary. So let's proceed first to the introduction. Nowadays, the global carbon dioxide emission from energy combustion and industrial process have been steadily increasing over the years, in which the major contributors are from the sector of electricity and heat generation, transportation and manufacturing and construction and building. Therefore, to eliminate or to address this emission, the hydrogen energy has emerged as a promising alternative source of energy in the future, because hydrogen is a clean and renewable and eco-friendly energy source that can be used in hydrogen fuel cells that can produce electricity efficiently. Unlike traditional fossil fuels, the hydrogen fuel cells is only emit water-based and heat, making them more efficient or more energy efficient and environmentally sustainable. We can extract hydrogen in several methods. Sorry. No. Sorry, there's something happened in my monitor. Let's see. Okay, there's something happened in my monitor. We can extract hydrogen in several methods with different environmental impacts. The first one is called gray hydrogen, in which the hydrogen extracted from natural gas promoted higher carbon emission. The second one is called blue hydrogen, also derived from natural gas and having lower carbon emission. And the third one is green hydrogen, in which the hydrogen extracted from water through electrolysis process using renewable electricity, promoting zero carbon emission. Therefore, among these three methods, the green hydrogen standout is a clean and sustainable solution in the global shift toward decarbonization. If we look at the global green hydrogen market and demand projection by 2050, it's expected to grow significantly and highlighting the long-term confidence in the global green hydrogen sector in the future. Simultaneously, the global hydrogen demand by sector also increased tenfold by 2050, with the primary contributor to this growth are from the sector of transportation, industrial sector, and power generation. Therefore, to meet the rising demand of hydrogen in the future, it is important to have a large-scale production of hydrogen from the cleaner source such as green hydrogen. To stabilize the mass production of hydrogen, we can store hydrogen in a liquid and solid and gas state. We can utilize liquid hydrogen in several applications such as in space industry, maritime shipping, and for hydrogen gas, typically we can use this one for hydrogen fuel cell such as transportation, stationary power generation, and residential and commercial building corresponding to their operational temperature condition. However, material exposed under hydrogen environment at different temperature may face some challenges, such as it can vary the hydrogen interaction with the materials, particularly under applied stress, that can cause of hydrogen embrittlement, which can degrade the mechanical properties and structural integrity of the material. That's why to have a huge production of hydrogen energy, it is important to find the most efficient and cost-effective material suitable in handling hydrogen environments. Nowadays, the austenitic stainless steel with FCC or structure or phase cubic centered structure is widely used in hydrogen services due to its excellent mechanical property, particularly at lower temperature. And however, some studies have shown that this material can undergo phase transformations from austenite to martensite at lower temperature after string. The performance of this material under hydrogen environment, it is important to observe its mechanical behavior in several factors, such as temperature, halogen pressure, and exposure of time or halogen diffusion rate. That's why the main goal of this study is to evaluate the halogen embrittlement behavior of austenitic stainless steel using our simple method, which is the small punch test, using two different halogen pressure based on the temperature conditions, in which 10 megapascal was used for lower temperature and cryogenic temperature, and 3 megapascal for elevated temperature. In addition, we also aim to examine how the material behaves in different deformation rate under halogen environment or different punch velocity corresponding to the different temperature condition. There are several techniques that has been developed in screening the material in gaseous halogen environment, but in this study, we mainly focus on our simple testing techniques, which is the NC2 small punch test under external halogen environment, in which this method involves compressive test in which the one-side surface of the specimen is directly exposed under external halogen environment during loading. This method is more efficient and cost-effective compared to the other method because it requires less amount of time, less amount of halogen, and small size of specimen to be used to conduct the test. In addition, using this method, we can easily establish the test environment such as pressure, temperature, and velocity. For the specimen preparation, our sample are done by wire cut process with this corresponding dimension, and we manually polish the one-side surface of this specimen using the abrasive paper to remove the impurities before exposing to halogen environment. And this is the construction of our simple test method developed at our university, in which the specimen is located between the upper and lower die, and we utilize the steel ball to punch the specimen while exposing to high pressure halogen environment using the puncher. And we utilize the pressure gauge to monitor the specific pressure of the gas during the test. And this is how the material deformed after applying the load. And as you can see, this is our various test setup in different temperature conditions under high pressure nitrogen halogen gas environment. At room temperature, we just simply expose the material into ambient temperature during the test. The load was applied using the AGIS Yumatsu or Universal Testing Machine. At lower temperature, with this corresponding temperature range, we utilize the liquid nitrogen to cool down the specimen inside the die, and we use the capsule container as our thermal insulator to prevent the heat loss and easily maintain the test temperature condition during the test. And we attach a thermocouple on the specimen surface to monitor its temperature during the test. And we conducted the test after the temperature stabilized within 10 minutes. At cryogenic temperature, we just simply submerge the dye into the liquid nitrogen, and after stabilizing the temperature, we conducted the test. For the test conditions we have done for the experiment, in the case of gas environment, we used two different gas, which is the nitrogen and hydrogen, in which the nitrogen gas was used to assess the HE susceptibility or halogen embrittlement susceptibility of the material exposed under halogen gas environment. For the gas pressure, we used 10 megapascal high pressure at lower temperature and cryogenic temperature, and 3 megapascal for elevated temperature. And to evaluate the deformation behaviors of the material under exposing to halogen environment, we implement 3 different types of punch velocity from 1.0 to 0.01 millimeter per minute. And we evaluate the halogen embrittlement behavior of the material in a wide temperature range from negative 196 degrees Celsius to 200 degrees Celsius. To quantitatively evaluate the edge susceptibility of stainless G0/L steel by SPT, we use three parameters. The first one is called SP energy, which derived from the area under the load displacement curve in nitrogen and halogen environment, in this parameter, we use the nitrogen load displacement curve to assess the HE behaviors of the material in the load displacement curve under halogen environment. As you can see, this is the typical fracture morphology analyzed by scanning electron microscope or SEM under nitrogen and halogen environment, in nitrogen environment it showed a large circular crack or plastic deformation, while in halogen environment it showed small ring-shaped cracks due to the hydrogen embrittlement effects. Therefore, by utilizing this recovered specimen, we obtained our two remaining parameters, such as the reduction of thickness or ROT and relative reduction of thickness or RRT, in which the reduction of thickness derived from the final thickness and initial thickness of the sample. The final thickness was measured the average thickness from the field spot region of the recovered specimen using the point micrometer. As you can see, this is the typical thickness that we obtained under nitrogen and halogen environment, in which thinner was observed under nitrogen compared to the halogen environment. Lastly, the relative reduction of thickness, which is derived from the ratio of reduction of thickness under halogen environment and nitrogen environment. And this parameter will be used to compare to the other method, which is from the relative reduction of area or RA by slow strain rate test or SSRT. As you can see, this is the load displacement curve obtained after SPT at various temperature conditions. When we lower the temperature from room temperature to negative 196 degrees Celsius, the maximum load or the strength of the materials increases under nitrogen environment due to the strain hardening at lower temperature. However, under halogen environment, severe halogen embrittlement was observed between room temperature and negative 60 degrees Celsius due to its low maximum load and fracture displacement at all punch velocity. But when we decrease the temperature from negative 100 to negative 150 degrees Celsius, the punch velocity effect was noticeable, in which the highest punch velocity showed the highest value compared to the lowest punch velocity. Therefore, there's an improvement of hydrogen embrittlement resistance at this temperature condition, particularly at highest punch velocity. And when we lower the temperature to negative 196 degrees Celsius, the low displacement curve obtained under hydrogen environment correspond to the nitrogen environment in all punch velocity, which is showing that there's no significant hydrogen embrittlement effect at this temperature condition. But when we increase the temperature from 50 degrees Celsius to 200 degrees Celsius, you can see that there's a continuous decrease in maximum load or material strength under nitrogen environment, but somehow under halogen environment it continuously increasing, and when it reached 100 degrees Celsius, the maximum load and fracture displacement under halogen environment correspond to the nitrogen environment, showing that there's the absence of halogen embrittlement effect at this temperature condition. If we look at the fracture morphologies obtained in different temperature conditions, under nitrogen environment, it showed a large circular crack or showing a large plastic deformation occurred in this material in different temperature conditions. And when we further observe the crack surface of this material, only dimple fracture was observed or ductile fracture in all temperature conditions. Under halogen environment, predominant dimple fracture was observed between negative 150 degrees Celsius and negative 196 degrees Celsius. at cryogenic temperature and between 100 degrees Celsius and 200 degrees Celsius at elevated temperature, showing that there's no significant hydrogen effects at this temperature condition. Moreover, ductile to brittle transition behavior due to HE influenced by punch velocity was observed at negative 120 degrees Celsius at cryogenic temperature and 70 degrees Celsius at elevated temperature from intergranular fracture or brittle fracture to dimple fracture or ductile fracture, in which the highest punch velocity showed the predominant dimple fracture and the lowest punch velocity showed an intergranular fracture. Moreover, small ring-shaped cracks and combination of quasi-cleavage and intergranular fracture was observed between negative 100 to room temperature, showing the severe hydrogen embrittlement effect at these temperature conditions at all punch velocity. If we look at the quantitative parameters results in evaluating the HE susceptibility of stainless steel at different temperatures, it shows that negligible hydrogen embrittlement effects was observed below negative 120 degrees Celsius at cryogenic temperature and over 70 degrees Celsius at elevated temperatures due to the value of hydrogen correspond to the value under nitrogen environment. In addition, significant hydrogen embrittlement effect was observed in the remaining test condition, especially between room temperature and negative 60 degrees Celsius, which show the severe hydrogen embrittlement in all punch velocity. And if we compare our results, RRT obtained by our SPT and to IRA obtained by SRT from other research group, it is showed that the similar extent hydrogen embrittlement behavior in different temperature range applications. Particularly when we compare our results at 1.0 millimeter per minute punch velocity by SPT. Therefore, we conclude that our simple testing method is reliable in screening the hydrogen embrittlement behaviors of stainless steel at different temperature conditions under high pressure hydrogen environment. Since some studies have shown that this material can undergo phase transformation, particularly at lower temperature, we evaluate the ferrite contents of this material from the deformed and undeformed region at different temperature conditions using the sample tested under nitrogen environment. And when we decrease the temperature, we found out that the ferrite contents continuously increasing on the deformed region, showing that there's an induced martensitic transformation occurred in this material during and after deformation. However, in the undeformed region, it showed the constant value, which is almost zero, or there's no variation of ferrite contents, showing that it keeps being austenitic phase at this condition, even though it exposed at different temperature condition. That's why if we compare the RRT results to the ferrite contents as a function of temperature, we found out that there's no hydrogen embrittlement effects occurred at elevated temperature over 100 degrees Celsius due to the low ferrite content, or there's no significant martensitic transformation occurred in this temperature temperature. And when we lower the temperature from 70 degrees Celsius to negative 60 degrees Celsius, there's a significant hydrogen embrittlement effect was observed due to the transition from austenite to martensitic phase. However, there's an improvement of hydrogen embrittlement resistance over below negative 60 degrees Celsius, even or despite the fully martensitic phase at this temperature condition. This is due to the changes of hydrogen diffusion rate or enhancement of twinning mechanism at cryogenic temperature. And when it reaches below negative 120 degrees Celsius, it does not give any hydrogen embrittlement effects in the material. Therefore, To improve or to enhance the HA resistance of this material, it is important to improve its austenitic phase stability, particularly at lower temperature, from 70 degrees Celsius to negative 120 degrees Celsius. As the summary, we confirm the effectiveness of our in situ SP test or SPT method in evaluating the halogen embrittlement behaviors of austenitic stainless steel at different temperature conditions, and it provides reliable and well-correspond halogen compatibility data, which is comparable to the other research group. And we obtained the punch velocity dependent behaviors at between negative 120 degrees Celsius and 70 degrees Celsius. And as we decrease the temperature, we obtain that the ferrite contents of this material continuously increases particularly from 70 degrees Celsius to negative 120 degrees Celsius, which promoted the severe halogen embrittlement effects in the material. And if this material exposed at elevated temperature over 100 degrees Celsius with lower ferrite contents, and cryogenic temperature below negative 120 degrees Celsius with high ferrite contents or martensitic phase after straining, it could not provide halogen embrittlement effects in the materials. Therefore, we conclude that the stainless steel L is good or can be applied in a halogen environment at higher temperature over 100 degrees Celsius and at cryogenic temperature below negative 120 degrees Celsius. That would be all. Thank you.
Okay, thank you very much, Engineer Pascua. Now the floor is open for the participants' questions. Okay, just raise your hand if you have any questions. All right.
Good afternoon, Engineer Pascua. I am Lovely May Nidwa from BS Mechanical Engineering, and here's my question. What is in situ method?
Thank you. I remember you. Okay, I'll show you the slide first.
I think you have a lot of memories here, no?
Yeah, I remember. Okay, so in situ, actually there are two types of methods, the ex situ and in situ method. In situ method, we actually evaluate the material exposing under external halogen environment, meaning the halogen comes from external to internal of the specimen. While the ex situ is that they use the electrochemical halogen charging, which is they diffuse in first the halogen in the material before conducting the test. Or the internal, it's in an internal halogen environment, and the in situ is under external halogen environment.
Thank you, sir.
Good thing Engineer Pascua still remembers Miss Nidwa.
Yeah,
Okay.
she was my previous student before.
All right. Okay, another question. Yes, we have another question. Okay, you go.
Good afternoon, everyone. Good afternoon, Engineer Pascua. I am Rica May Sanchez, fourth-year student at Aurora State College of Technology. Since we talk about evaluation of materials under hydrogen environment using a small punch testing method, here's my question po. How can a small punch testing result be used to improve the safety and reliability of hydrogen-related infrastructure and equipment?
Okay, so okay. As I have said, we use this small in situ small punchers with a small scale method. We didn't use a large scale method. So in this case, we lowered the cost and we save time to do this experiment, and especially we designed the small punch test in order to evaluate the small size of the specimen that will be conducted under external hydrogen environment. And especially, we use the small amount of hydrogen to observe the hydrogen embrittlement behaviors of this material, unlike the other method.
Okay.
Thank you, sir.
Yeah, we have one more question at the back, or in the middle.
Good afternoon, sir. My name is Jan Marlon B. Mariano, and I'm currently a student here in ASCOT, currently taking Bachelor of Science in Civil Engineering, sir. My question is, for your testing conditions, why did you specifically choose 10 MPa as your pressure for temperatures negative 196 degrees Celsius and 2 room temperature? Why not 11 MPa, 12 MPa, 20 MPa? And for the temperatures 50 degrees Celsius and above, why did you choose 3 MPa? That's all.
Thank you so much. Actually, these pressures are correspond to the actual hydrogen services application, in which we use a lower pressure at elevated temperature because it can stable its gas state at lower pressure at higher temperature. And at cryogenic temperature, it required higher pressure to stabilize the liquid state. That's why we use 10 megapascal.
Thank you, sir.
Okay. We do have one more question from the Dean of SOE, Sir Richard. Eto na si Dr. Alkin Gorospe. Recitation.
Hello, good afternoon, Sir Richard Pascuan. Yeah, I know that that kind of experiment is a very tedious one, right? Yeah, so we know the hardship that you're. So my question is it possible for you to incorporate CAD simulation to the study so that medyo hindi ka mahirapan doon sa experiment, because I know it's a very difficult experiment. Yeah, and if yes, mayroon ba tayo dyan sa laboratory, or are we equipped to do so? Thank you.
Okay, thank you, sir. Yes, sir. It's possible. Nowadays, we are doing the simulation using the ANSYS software. As you can see in my presentation before. Okay. Hindi na ako, sir. Okay. As you can see in my presentation. Okay. Yeah. As you can see in my presentation, this is our data using the ANSYS analysis, which we measure the stress distribution of the materials after the applying the deformation. So yeah, but in this case, there's some parameters that we can there's some parameters that we can okay. There's some parameters that we can sorry. Merong mga parameters sir dito na limited na hindi natin kayang i-simulate. For example, yung temperature, the temperature applications like in cryogenic temperature, so it's not possible. But at room temperature, it's possible, sir, to obtain the stress distribution of the materials while flying the load on the material.
Okay, thank you very much and regards dyan sa atin. Thank you.
Okay, I guess no more further questions, no? So, okay, we will now award the Certificate of Appreciation to Engineer Pascua, and here's the content of the certificate. Republic of the Philippines, Aurora State College of Technology, Barangay Zabali, Baler, Aurora. The Certificate of Appreciation is given to Engineer Richard Gonzalez Pascua for your dedicated participation as guest speaker in the cross-border engineering innovation at Aurora State College of Technology, ASCOT Hostel, Barangay Zabali, Baler, Aurora on April 29, 2025. Given this 29th day of April 2025. Signed, Engineer Alking Bigo Rospe, the Director of Research and Development Office. Signed, the Vice President for Academic Affairs, Dr. Maluz F. Cabatan, and signed, the SEC President to Dr. Renato G. Reyes. Give him a round of applause, please. Once again, thank you so much, Sir Richard, and we're looking forward to see you again here at ASCOT.
We miss you, Sir Richard here. Okay, now let's move on. Now let's move on to our 8th speaker. Our 8th speaker is an operation lead supervisor, energy manager, University of Santo Tomas, Philippines. He will share a topic on industrial HVAC system innovation, fluid flow analysis through CFD simulation. Let's give him a round of applause. Engineer Sherwin Mina.
Hello everyone. Thank you for that very nice introduction to me. Am I audible?
Yes, sir. Loud and clear, sir.
Are you viewing my presentation or the presentation?
Yes, we can see it,
Okay,
sir.
okay. Without further ado, I'll start na. Again, I will introduce myself. I'm Engineer Sherwin Mina. Currently, as a graduate student at Napo University, taking MSME with a major in sustainable technology and renewable technologies. Start with, this is my topic, industrial HVAC system innovations and fluid flow analysis through CFD simulation. Sorry. So as an outline, on my presentation, we will learn what this CFD is, how it is work, what is application. Next, the benefits of CFD integrated design, especially on HVAC. The application of CFD with focus on industrial HVAC system. How CFD simulation process in HVAC design is performed. And the presentation of case study result and conclusion and recommendation for future studies. So, as an introduction, let me show this. Any one of you is familiar with this? What you can see in the screen is the Sustainable Development Goals, also known as the Global Goals, that are adopted by United Nations in 2015 as a universal call to action to end poverty, protect the planet, and ensure that by 2030, all people enjoy peace and prosperity. So my research tackled 4 of the goals. First is the affordable and clean energy. By improving HVAC energy efficiency through CFD optimization, our study helps reduce overall energy consumption, promoting sustainable energy use. The second is industry innovation and infrastructure. So introducing CFD simulations into HVAC designs promote innovation in industrial practices, enhancing infrastructure performance and sustainability. The third one is sustainable cities and communities. Energy efficient, well-ventilated industrial facilities contribute to building safer, healthier, and more sustainable working environment and urban areas. And the last one is the climate action. Reducing industrial energy waste support global efforts to combat climate change by lowering greenhouse gases emissions. As Engineer Pasco said earlier, buildings are one of the main contributors of CO2 emissions in our world today. Next, the problem statement. So, here's the first, limited precision in traditional HVAC design. Conventional HVAC design approaches often rely on generalized assumption, yung rule of the thumb, leading to inefficient airflow distribution and increased energy consumption in industrial setting. As they say, a kilowatt of energy that is conserved is 100 times better of a kilowatt energy that is produced. Second, underutilization of CFD technology in HVAC optimization. Despite its potential computational fluid dynamics, simulation is not widely integrated into standard HVAC design processes, resulting in missed opportunities in performance enhancement and cost savings. Next, energy inefficiencies and operational cost. Inefficient HVAC system layouts and ventilation strategies contribute significantly to high operational cost and excessive energy usage, especially in energy-intensive industrial environments. As the result of the research of International Energy Agency last 2022, cooling of buildings contribute about 30% of overall energy consumption of the whole building. So imagine that. Lastly, for indoor air quality and thermal comfort, nowadays this HVAC system design focuses on this, not only in cooling. Inadequate analysis of airflow patterns lead to poor indoor air quality and uneven thermal conditions affecting worker productivity, equipment reliability, and regulatory compliance. So why it is crucial to prioritize building and their mechanical system to be optimized? So I think this is the one information that I have mentioned earlier. Significant carbon emissions. The total global carbon emissions in 2023 was 37.4 gigatons. The building sector is responsible for approximately 39% of global CO2 emissions, primarily from energy consumption for cooling systems. Next, high energy consumption. Mechanical systems, particularly heating, ventilation, and air conditioning, in our country, air conditioning, accounts for nearly 30% of total energy consumption in buildings. Resilience and adaptability. As urbanization accelerates and climate patterns shift, building must design to adapt to changing environmental conditions. Integrating advanced mechanical system can enhance building resilience to extreme weather events, thereby safeguarding both infrastructure and occupants. This resilience and adaptability has been seen on the past few years when we experienced the pandemic. Not all, but generally, HVAC system are not, here in the Philippines, are not ready for that. We focus on it when we are designing on cooling, but not on overall performance that tackles contaminants on the buildings. And lastly, document health and comfort. Our buildings' current mechanical systems are not built to adapt or combat the effect of rapid urbanization, such as heat island effect, which is tackled earlier, which causing occupants to experience sick building syndrome. Mechanical systems are crucial for maintaining indoor air quality and thermal comfort, which directly affect occupant productivity and health. So our objective in conducting this study are as follows. First is to analyze airflow and temperature distribution. By using CFD simulations, researchers aim to understand airflow patterns and temperature regulations in buildings, aiming to reduce energy consumption and improve thermal comfort. Second is to optimize HVAC system performance by identifying how CFD can be used to design more efficient HVAC system that reduce energy use while maintaining effective temperature and control and air quality. Third is evaluate passive and active design strategies. To evaluate the impact of CFD-driven HVAC innovations on energy consumption and indoor environmental one. Lastly, support global sustainability goals, as I mentioned earlier. Demonstrate how optimizing mechanical system with CFD contributes to global efforts to reduce carbon emissions and achieve climate goals such as limiting the global temperature rise. On our topic, what is computational fluid dynamics? So, computational fluid dynamics, or so-called CFD, is a branch of fluid mechanics that uses numerical methods and algorithms to solve and analyze problems involving fluid flows, heat transfers, and other physical phenomena. In HVAC, generally, CFD is a simulation-based tool used to predict fluid behavior, airflow, temperature distribution, and contaminant spread within HVAC system. It uses mathematical models and numerical analysis to simulate how air moves through space, how heat is transferred, and how the pollutants of contaminants are distributed. So some applications of CFD are seen: engineering and design, HVAC system. We can also use it in environmental engineering and chemical processes engineering. The last presenter, this topic can be analyzed using ANSYS. That's CFD software. Just like this. Next. Benefits of CFD integrated design. What are those? So first is the cost-effective design. CFD allows testing of various design configurations without the need of physical prototypes, saving both time and money in product development. This is the most advantage of CFD compared to the manual testing and manual building of prototypes. So next, improve system performance. It helps to optimize design by simulating multiple scenarios and identifying the most efficient solution before any physical changes are made. Next, increase safety by simulating undesirable conditions such as high pressure or high temperature scenarios. CFD helps to ensure systems are designed safely and effectively. Lastly, detailed analysis. CFD provides detailed insight into flow characteristics, heat distribution, and other phenomena that are difficult to analyze through traditional experimental methods. The application of CFD in industrial HVAC system. First, airflow distribution planning. CFD helps in designing and analyzing airflow patterns in rooms or large spaces from a single duct or to a whole building. You can simulate its HVAC system. You can analyze how effective your design without building any prototypes. It identifies issues such as dead zones or poorly circulated air and allows for adjustments of in diffuser placement, air velocity, and ductwork designs. Next, thermal comfort optimization. By simulating heat distribution and temperature gradients, CFD helps in improving PMV or the predicted mean vote values. This scale can be found in ASHRAE 55, ensuring comfortable conditions for occupants, especially in controlled environment like hospitals and in clean rooms. Third, contaminant removal. CFD is used to track contaminant transport and optimize air changes, ensuring that pollutants are quickly removed from sensitive environment like operating rooms and ICUs. It helps to determine the ideal placement of exhaust and filters. So lastly, energy efficiency improvement. CFD optimization can reduce energy consumption without sacrificing occupant comfort by improving air distribution, reducing fan power requirements, and minimizing heat loss or gain, ultimately leading to more sustainable systems. So that's all of the advantage of CFD. So how CFD works? So, CFD is a powerful tool for simulating fluid flow, heat transfer, and particle movement within HVAC system. The process involves, first is geometrical modeling. Second, when you achieve the digital twin, you can proceed to meshing. Then, assignment of boundary conditions, and followed by setting up solver settings and the post-processing steps. So that's 12 in this. So, first is the geometrical modeling. Geometrical modeling is the first step in CFD simulations, where the digital representation of HVAC system and its surrounding environment is created. The key element includes system layout, environment material features, and boundary division. Take this residential house as an example. Using 3D softwares, you can create the digital twin of the area or the building you want to analyze and assign all of the real world materials used, such as hollow blocks, tiles, and so on and so forth. So, next. So, geometrical model. Yeah, yan ang itsura. This is how it looks when you entered it on CFD simulations. This is its geometrical representation. So, meshing. Meshing is the process of dividing the geometric model into smaller, manageable cells to solve fluid dynamics equation. The quality of mesh directly impacts the accuracy of simulations. The key aspects include mesh type, either triangle, quadrangle, two-dimensional, and mesh density. Mesh type, three-dimensional, tetrahedron, hexahedron, pyramid, or wedge. This is how it looks when you divide it into mesh, your 3D representation or your digital twin. And when you analyze, this is how. Take it an example. When you analyze this one big square, comparing to analyzing each of that cells, you can get more information about the area, especially when analyzing fluid flows around this boundary or region. So next, boundary conditions. Boundary constraints applied at the boundaries of the simulations domain, defining how fluid interacts with the surfaces. Example, walls, inlets, outlets. Typically, types include velocity, pressure, temperatures, R values, heat flux, etc. This symbol indicating it has been assigned boundary conditions, just like this. This symbol represents velocity inlet number 5, which is boundary condition. Velocity inlet, velocity type, fixed value. This is velocity, x, y, and z, and turbulence, automatic. The temperature is 22 degrees, and so on and so forth. Assigned as air-conditioned free supply. Third, setting up CFD settings in CFD. So solver settings are critical for ensuring that the solution is to a given problem is accurate, efficient, and converges properly. The more you input or assign on the later step, the more accurate the CFD simulation will give you. This setting governs how the CFD solver will approach the simulation, including the algorithm used for solving the governing equations, such as the Navier-Stokes equations, and the criteria for determining when the solution is sufficiently accurate. Here, the solver we are using is the convective heat transfer analysis. So, post-processing in CFD. Post-processing is a crucial step in CFD simulation. It involves analyzing and visualizing the simulation results to interpret the flow behavior, identify problem areas, and assess performance. Here's a breakdown of the key post-processing techniques. So, there are five post-processing techniques. First is visualization. You can see in this contours, streamlines, vector plots, isosurface, and for flow patterns. Quantitative analysis, flow rates, pressure drops, and temperature distributions in a certain area. Data extraction, surface integrals, point monitoring, domain-wide integrals, animation and time analysis, and report generation, custom reports comparison plots for different scenarios. So this is how it looks like. From this is the result of my simulation runs on residential HVAC simulations. This is the results animation. You can see what is the effect of natural ventilation that infiltrates to this entrance to the AC system here. Also, we can identify the hot spot of the area, which is in this area where the velocity or the air is filled, because the air doesn't reach this part of the room. For further analysis, so you can area monitoring. As you can see, you can pinpoint area on the digital twin, and it will show you what temperature of the area. As an example, in region 1, the minimum temperature in region 1 is 22 to 23. The maximum on this area is the temperature is 22. You will see the temperature profile of whole area. This slice is on x-axis of the room. This is the y-axis. This is the velocity magnitude of the air in the area. The blue indicates the still air, which we have seen here. Meron din tayo dito. And the maximum velocity is 0.78 meter per second, which is the desirable air velocity for human comfort. So lastly, this is the y-axis. In the y-axis, velocity magnitude of air. This has a greatest velocity of the area because this is the supply or the discharge of the split type air conditioning system. So this area, we have 0 here. This tail air or stale area, these areas must be reanalyzed. The unit must be relocated to address these problems. There are a lot of zeros. And over velocity areas. So that's it. Innovative industrial HVAC system strategies for enhanced airflow and energy efficiency. First, smart airflow control or the adaptive VAVs. Energy recovery optimization, hybrid ventilation models, and occupant-focused air delivery. All of this system can be optimized by enhancing CFD in the design phase of the system. So, Industrial facility energy consumption. So this is the survey for our initial conditions. Commercial building heavily rely on electricity during working hours within around 60% of their daily energy consumption, occurring during the daytime. This distinct pattern influenced the overall energy consumption of the respective sectors. In industrial setting, electricity consumption start to rise, peak and fall at 6 a.m. to 8 p.m. time. Here, some case study results, CFD simulation finding insights and suggestion, office and waiting area. So this is our digital twin with all of its occupants, zone 1, zone 2, and zone 3. These real squares are the diffusers and the exhausts, and these are the simulation boundary settings. Our ambient temperature is 31 degrees Celsius. Internal operating temperature is 22. Internally relative humidity, this is the desired 50%. RH, then the floor area, 150 meters squared, divided by 3 zones. Zone 1, the lobby. Zone 2 and 3 is the office area. And external wall composition. So this is the wall composition, cement plaster, concrete blocks, and the internal is cement plaster. So this is the existing, and the proposed is the integration of bio-PCM or the bio-phase change materials integrated in concrete for the proposed wall setup. So floor to ceiling height is 2,400 mm, 2.4 meter, and the air exchange standard is 4 from the ASHRAE 170 guidelines, minimum requirement for general examination room. So when we simulate the existing layout, with the current setup, CFD results indicate areas with inadequate air circulation, results in temperature discrepancies in the area. Yeah, those spots in circles on the locations indicate no air movement. So these problems are the ones we cannot see without the aid of CFD. So how we can resolve it? So design parameters intervention, we have to introduce some design parameters intervention for the zone 1, zone 2, zone 3. For the walls, we introduce bio-PCM. For the supply air, we increase the supply from 100, 200 to 200, 200 liter per second respectively. The exhaust system is retained. Diffuser count, it was increased. Diffuser location relocated. Diffuser row from 60 degrees to 45. Diffuser velocity from 2 to 2.9. So to improve this, it is suggested to adjust the location layout of the size of vents, diffuser, and grills to the optimum dimension based on the occupant location requirements. So ito, 2.5, 2.7, and 2.10. These are desirable, which is optimum diffuser distance, center to center, distance to each other, and optimum diffuser distance to the wall. All of this data is obtained from the CFD simulations without producing any physical example of the building. We obtain this and we can apply it to the design prior to the building of the physical HVAC system. So on the duct design, square or rectangular ducts are popularly used in the Philippines, but the CFD simulation confirmed that the round ducts are more ideal to use when compared. Disadvantages are as follows: reduced air resistance, enhanced airflow, and energy conservation through operational efficiency. So, yeah. As you can see, square or rectangular ducts, the airflow in the ducts have many eddies or the small swirling airflow turbulent vortices. The effect of these eddies are increased pressure losses, non-uniform air distribution, increased noise levels, A higher risk of particulate deposition, reducing heat transfer efficiency. Unlike to these round ducts, the only part that have eddies are this curve or the elbows. So the advisable to use when designing duct systems for residential or industrial settings is round ducts. So on walls, PCM integrated walls, the figure 2, shows great potential due to its improvement, lower U value, which is very important when you are designing insulations or materials for your buildings. When it comes to temperature management, thermal management of your building. When compared to a conventional wall setup, figure 1, results show that such walls greatly reduce the building internal heat gain, resulting in the reduced thermal load in the. So, yeah. From 2.093, the PCM reduced the U value to 1.872. Post-simulation result, the first simulation result, current setup, as we see, there are many stale areas. The final simulation test result with the design adjustments and design interventions, mostly green na. So we address those. We remove the problems. Comparison of unoptimized versus optimized setup, the predictive mean vote and contaminant extraction. This is as type 50 PND scale value. Very cold, -3. Cold is slightly cool. Neutral is slightly warm, and hot. When we are designing HVAC system, we are aiming to this scale 0. As you can see, on the first on unoptimized setup, we have number 2. But the contaminants extraction effectivity, we have low, high. Comparing to the optimized, we are on number 1, slightly cold. Next. So subject area energy reading comparison, baseline and proposed design. So the table projected energy reading of the area before and after applications of suggested design considerations to answer the concerns identified by CFD simulation. As we can see, in the office hours, where the areas is being utilized, here, from 6 affiliate to 8 p.m. We can see noticeable reduction on energy reduction, improving the importance of CFD assisted design to terms energy efficiency conservation compared to the baseline. This is the proposed setup, which have lower energy consumption compared to this. Almost 15% drop on the area's daily electrical consumption. So, area performance comparison results, simulation-based results. All of these are simulation-based results. In area mixing efficiency, existing layout for air distribution, stagnant zone. As we can, in optimized layout, 30% improvement in air mixing. Optimization implemented. Reposition supply diffusers and exhaust grills for more even airflow. Improvement 30%. Particle removal rate is in our existing layout is low air, change rate, long time removal. On the optimized layout, 22% faster particle removal. Contaminant transport, inconsistent, inefficient airflow. For the optimized layout, efficient airflow with optimized diffuser and grill placement. The optimization implemented, optimized airflow pathways and ventilation problem. We used round ducts. Improvement, more efficient contaminant removal. Convergence stability, moderate, required adjustment for the optimized layout, high stability, minimal adjustments. Then optimize implemented, improve mesh quality boundary. More on the simulation now. So conclusion and recommendation. In conclusion, HVAC system can achieve smarter airflow control, higher energy efficiency, and healthier indoor environment. By optimizing designs before implementation, we not only enhance performance but also create safer, sustainable spaces, especially critical in healthcare and other high-hazard facilities like hospitals. As a recommendations, continue to utilize computational fluid dynamic simulations in building design and retrofit. Planning is paramount for achieving and maintaining optimal efficiency, sustainability, and occupant comfort. By harnessing the power of CFD, we can precisely visualize and analyze airflow, temperature distributions, and energy consumption patterns within built environments. Therefore, the continued utilization of CFD simulation represents a forward-thinking strategy that aligns with the goals of modern, sustainable architecture and engineering practices, ensuring that our buildings are not fit for today's challenges, but also adaptable for future demands. Recommendations for future studies. First, expand safety application in other industrial settings, improve of hybrid cooling systems, real-time CFD simulations, development of more accurate predictive models, integration of Internet of Things and smart building systems, and hospital-specific optimization, such as giving importance to the design of hospitals. So another project, much more bigger than I want to show you this. This is the whole area of UST. This is the hospital. This is the air velocity of the area for the whole area. This is about 1 square kilometer. You can see how air reacts with that all buildings around. We use the data here to evaluate the air infiltration and use this as a passive ventilation system. Next is the all year round sunlight, sun hours. That's it. Last, as a final message, let's build smarter, healthier spaces together. Thank you. Thank you for having me. Yep.
Okay, thank you so much, Engineer Mina. Okay, the floor is now open for your questions. Okay, is there any questions here? Yes, we have a question here.
Good afternoon, Engineer Mina. I am Kimberly Abserano from Mechanical Engineering Program. I have a question here. Since we were talking about industrial HVAC system innovation, fluid flow analysis through CFD simulation, knowing that CFD is used for modeling the airflow and temperature distribution and other factors, what are the limitations of CFD in predicting real-world HVAC system behavior po?
Limitations. Our technology, the CFD technology is broad, napakalawak. As long as you can provide all boundary conditions and initial conditions, as long as you can model the system, I think it has virtually no limitations. But there is when the great limitation is the initial and boundary conditions. If you don't have the boundary condition and the initial conditions, you can have the results you decide to study.
Thank you po, Engineer Mina. I was about to ask if you already applied it on UST Hospital, but you showed it already po. So that's all po. Thank you.
Thank you so much. Is there any questions? I guess there's no other question. There is? Okay. So now let's move on to the awarding of certificate for engineer. Let me read the content first. Republic of the Philippines, Aurora State College of Technology, Barangay Zabali, 3200, Baler, Aurora, Philippines. This certificate of appreciation is given to Engineer Sherwin Mina for your dedicated participation as guest speaker in the cross-border engineering innovation at Aurora State College of Technology, ASCOT Hostel, Barangay Zabali, Baler, Aurora on April 29, 2025. Given this 29th day of April 2025, signed the Director of Research and Development Office, Engineer Alking B. Gorospe, signed Vice President for Academic Affairs, Malus F. Cabatan, signed SUC President to Renato G. Reyes. Let's give him a round of applause.
Thank you.
Again, thank you, Engineer Sherwin Mina.
Thank you, thank you.
All right, our ninth speaker is Engineer Marvin C. Valentin, a PhD student at Wrocław University of Environmental and Life Sciences, Poland, and Assistant Professor 1 at Benguet State University, Philippines. Let's all give a warm welcome to Engineer Marvin C. Valentin as he shares his insights on pursuing engineering as a career beyond border from the perspective of a young Filipino engineer studying abroad. Hello, engineer. So this is a pre-recorded video presentation of the topic of Engineer Valentin. So let us all watch and listen.
It's very important when you are designing insulations or materials for your buildings. When it comes to temperature management, thermal management of your building. When compared to a conventional wall setup, figure 1, results show that such walls greatly reduce the building internal heat gain, resulting in a reduced thermal load in the so yeah. From 2.093, the PCM reduced its value to 1.872.
All right. Looks like we're having a technical difficulties here. Please bear with us. Yung mga papasalamatan.
Neutral is slightly warm, warm. But when we are designing HVAC system, we are aiming to this scale 0. As you can see, on the first and on unoptimized setup, we have number 2. But
good morning to
the contaminants extraction
good morning
effectivity,
to everyone.
we have
I send
low,
my warmest
high.
greet.
Cut mo muna. Sige po, salamat muna tayo.
All right, while waiting, we would like to thank once again our co-organizers for this webinar. The Pampanga State Agricultural University, President Ramon Magsaysay State University, Polytechnic University of the Philippines, Occidental Mindoro State College,
Bataan Peninsula State University, JSPS Alumni Association of the Philippines, Japan Society for the Promotion of Science, Bangkok Office, Nueva Ecija University of Science and Technology. Again, thank you very much.
and of course to the companies and the SUCs affiliated SUCs and companies in this webinar. We have the Benguet State University, the De La Salle University, University of Santo Tomas, Gyeongguk National University, Rocklo University, the University of Tokyo, Sejong University, and Latham, the Pool Company. Thank you very much.
And of course, we would like to thank our speakers. So we have Dr. Masharu Lincoln, Professor Yutaka Kaizu, Dr. Julius Flores, Dr. Michael De Leon, Dr. Crisabel Jane Rubio, Dr. Kiran Shinde, Engineer Richard Pasqua, Engineer Sherwin Mina, Engineer Marvin Valentin, and Engineer Dr. Susan Gallardo. Thank you so much for your time and sharing your expertise here in our webinar.
All right.
Long time removal,
A graduate study or career.
unoptimized efficient
Important
airflow.
to maintain a
For
good
the
network
optimized layout,
among these
efficient airflow
aspects.
with optimized
For
TPS.
From Benguet State
Good
University,
morning to everyone. I send my warmest greetings to each and every one of you from Poland, the heart of Europe. I also extend my greetings to Dr. Renato G. Reyes, the President of Aurora State College of Technology. Today, I am happy to be part of this webinar organized by the School of Engineering of the Aurora State College of Technology for me to share my journey as a young Filipino engineer who chose to pursue an engineering career beyond the borders of our home country. My name is Marvin Valentin. I am a fourth-year PhD student in the discipline of environmental engineering, mining and energy at Wrocław University of Environmental Life Sciences in Poland. Before, I once thought that pursuing advanced graduate studies or a career in engineering abroad was a far-off dream, something reserved to few individuals. Today, I stand before you as someone who is currently pursuing a PhD in engineering overseas, not because I had everything figured out, but because I took one brave step at a time. This presentation isn't just about my academic path. It's about the mindset, the challenges, the opportunities, and most importantly, the purpose behind taking this journey beyond our borders. Whether you are a student, a young professional, or someone simply curious about what lies beyond, I hope this gives you insight and inspiration. Let's dive into what it means to be a Filipino engineer in the global arena and how we can all carry our identity wherever we are in the world. Pursuing a graduate study or career abroad is not a one-day dream. It comes with a long time preparation, diligence, and purpose. During the application, we may encounter rejection. However, this is an important component of a good preparation. During my lengthy preparation, I had the chance to face different committees, and I have come to learn one important thing I am frequently asked for, and it's about telling them your beautiful life story. What have you done to deserve such aspiration? And what qualities you have to assure that you will deliver effectively the demand of the situation. Considering the network map that summarizes our personality, which most appropriately describe our fitness to enter a graduate study or career abroad. It shows that we have different aspects of our personalities, our lives, and it is important to maintain a good network among these aspects for us to promote a well-rounded and well-balanced personality that at least give the demand of studying or pursuing a career in other countries. As I proceed with my presentation, I would like to give you a brief background of my scientific research here in Poland. The focus of my research is on the application of carbon materials like biochar or hydrochar to enhance anaerobic digestion process. In particular, the anaerobic digestion is carried out by centropic microorganisms starting from the hydrolysis to the methanogenesis stage. The efficient electron transfer among these centropic microorganisms is known to enhance the anaerobic digestion performance. In addition, biochar application promotes the so-called direct interspecies electron transfer phenomena in the ED process. I would like to invite your attention in the network map presented on the screen. It shows here that biochar is one of the frequently cited keywords among the recently published articles, and there are various networks that are linked to biochar, and one of the common keywords is the anaerobic digestion. This indicates that biochar and anaerobic digestion is currently an interesting topic in the field of anaerobic digestion. In addition, my research work is also focused on the biological aspect in the anaerobic digestion reactor. So we have materials like biochar, the substrate, and the inoculum. And we basically mix this together at a certain ratio known as the inoculum to substrate ratio, or the ISR. And we study how the substrate and the inoculum behaves during the process, including the change in the microbial community of the process. In my case, there were several factors I considered when I decided to study abroad. Number one is the inspiration. Behind the natural and inviting prestige of studying abroad, I have met several mentors who earned their graduate studies abroad. Their stories fueled my inspiration to consider studying abroad one day. As I perceive, the path is really full of challenges. My attention is divided between fear and excitement. However, when I found my purpose in the academy, I experienced how difficult to teach. I thought that when you love what you are doing, then it is but natural that everything will follow smoothly. It wasn't like that in my situation. It seems that there is always a vacuum inside me. I believe that the foundation of an effective educator is quality and relevant academic training. I admit that I lack these elements. I felt that this vacuum can be filled when I pursue a graduate study abroad. Another factor is choosing the right university and also the right country. Choosing the right university could be very challenging. It depends on various factors such as the availability of scholarships, field of specialization, and personal preferences. At times, you may get accepted into a university of your choice or maybe your dream country, but the funding could be limited. On the other hand, you might have a scholarship, but it may only support limited universities. Or you may have both, but the situation doesn't permit you at all. I had this experience when I got accepted to the University of California in Davis, but there was not enough funding to support my graduate study. At some point, I got accepted in one of the most prestigious scholarships, the Fulbright Scholarship Program. However, the situation didn't allow me to leave the Philippines during that time. Later, I learned that the simplified and most legit way to get your destined university is to keep moving, learn the requirements, and do your best to meet the qualifications. Strengthen your academic and research background, build a story that you can tell to the committee, especially during the interview or when you write your application essays. Another is the overcoming of doubts and fears before leaving the Philippines. Leaving the Philippines is another challenge, especially because we have these close family ties. To embark on research works in a foreign land come with the sacrifice to leave our family behind and miss a lot of opportunities. For example, if you are a parent, then you might provide the best care to your children when you are with them. That alone is a very expensive social cost in exchange for staying in another country. No number of resources can compensate such loss. In the name of progress and development, we take new paths with the hope that it will bring great results to our family, to our university, and of course, to our country. Let me give you an idea about the few challenges that I encountered during the first time I arrived in a foreign land. Number one is the academic challenge, where there is a different teaching styles and even research expectations. Studying engineering abroad is both exciting and intimidating, especially rooting from the Philippines, where our teaching styles can be quite different. During my first semester, I realized that learning wasn't just about memorizing formulas anymore. Professors expected us to challenge ideas, ask questions, and take ownership of our learning. Research was also a big leap. Back home, research often comes later in your studies, while in abroad, it's woven into the fabric of the curriculum. I found myself in the laboratory where I didn't just follow instructions. I had to design experiments, interpret unexpected results, and even defend my hypothesis. The workload of working in the academy abroad can be very intense, especially for a foreigner like me. But I learned to manage it by developing better time management and leaning on support systems such as study groups and establishing collaboration among my colleagues in the laboratory. Second is cultural adaptation. At first, even casual conversation felt like decoding puzzles for me. People spoke fast, used idioms I didn't understand, and referenced pop culture I hadn't grown up with. But language barriers gradually faded as I pushed myself to join discussions, students' organizations, and university-organized activities. Finally, let us discuss about professional identity. Living and learning in a new environment has expanded my perspective. I now think about engineering not just in technical terms, but as a global responsibility. I have collaborated with people from different countries, seen how engineering solutions vary depending on context, and realized how important it is to design with inclusivity in mind. More than that, being a Filipino engineer abroad made me realize how valuable our resilience, creativity, and warmth are in the global workforce. We bring a unique voice to the table, and the world needs it. While it is true that there is a challenge for pursuing engineering career abroad, but there is a rewarding opportunity in demand for engineers in the global scenario. Across continents, engineers are needed in almost every sector like civil engineering, mechanical, electrical, software, and especially now in emerging fields like renewable energy, artificial intelligence, biomedical engineering, and data science. Countries in Europe are actively recruiting skilled engineers. There is a talent shortage, and Filipino engineers are well positioned to help fill that gap. Our training is strong, our English proficiency is a plus, and our adaptability makes us quick learners in new environments. Studying or working abroad helps us develop more than just technical expertise. It sharpens our soft skills, cross-cultural communication, and global mindset. We begin to see problems through different lenses, influenced by diverse perspectives. That kind of experience isn't just valuable, it's sought after. Many employers view international training as a proof of independence, initiative, and the ability to thrive in a challenging environment. Another is that one major benefit of studying or working abroad is access to networks. Professors, researchers, professionals from all over the world. Attending conferences, joining international engineering societies, or collaborating on research projects can open doors to internships, job offers, and even startup opportunities. Networking isn't just about who you know. It's about showing up, sharing your ideas, and building a professional presence that reaches beyond borders. And finally, let's celebrate what we bring to the table as Filipinos. We are known for being resilient. We adapt, we endure, and we rise to the occasion. We are resourceful, creative, and incredibly hardworking. We value teamwork, respect, and community, qualities that make us not only strong engineers, but strong colleagues. In the global workforce, these traits stand out. Employers remember the engineer who solved the problem under pressure, the one who stayed late to support a teammate, the one who showed heart, not just skill. And this is the quality of a Filipino engineer. At some point, while studying in Europe, I received various offers to consider working as an assistant professor in the university and also joining research project that is funded by the European Union. Not only me, but including my family and even also my wife to work as a professor in Europe. I believe that this offer is because of the resilience, the good quality that we show as a Filipino engineer, and that's why opportunities are catching with us. I heard before that if there is no opportunity, then we should create opportunity. For me, it is happening that opportunities are catching me. Well, probably because I tried to prepare or manage to prepare myself and acquire good qualities, and people took notice of these qualities, and that's why they are willing to even give me an offer, not only for me, but for my family. This is, I think, an exact example of what Filipino can bring to the world. And I am sure it will also happen to every engineers and the Aurora State College of Technology. At this juncture, I would like to give you an idea about the structure of the graduate study in my university in Poland. And this is a rich map that shows the important elements of my PhD program. What I like most in this structure is that our university supports professional development activities to ensure that PhD students will be able to acquire relevant skills and knowledge to successfully complete the PhD research. This professional development includes generous funding from the university to send students outside the country or even in other universities where they can perform research activities, internship, and even mentoring that would support the successful implementation of the PhD program. I enjoy so much this kind of structure because it helps develop my scientific skills, my academic skills, and also my networks and communication.
All right, thank you so much. That's a very informative presentation from Engineer Valentin, especially to those engineers planning to study abroad. Okay, so much tips and information. Now, for the certificate of appreciation. Okay. Right. Okay, to show our appreciation to Engineer Valentin, here's the content of the certificate. Republic of the Philippines, Aurora State College of Technology, Barangay Zabali, Baler, Aurora. This certificate of appreciation is given to Engineer Marvin C. Valentin for your dedicated participation as guest in the cross-border engineering innovation at Aurora State College of Technology, ASCOT Hostel, Barangay Zabali, Baler, Aurora, on April 29, 2025. Given this 29th day of April 2025, signed Engineer Alking B. Gorospre, the Director of Research and Development Office, signed Dr. Maluz F. Cabatan, the Vice President for Academic Affairs, and signed Dr. Renata G. Reyes, the SUC President too. Once again, thank you, Engineer Valentin.
Our last but definitely not the least is Dr. Susan Manalstas Gallardo, a University Fellow de la Salle, University of the Philippines. Dr. Susan, drawing from extensive experience and research, will share valuable insights on AUN SIDNet collaborative research in chemical engineering, experiences in cross-border innovation. Again, let's give her a round of applause.
Good afternoon to everyone. So I am here to present to you a talk about AUN SIDNet collaborative research in chemical engineering, experiences in cross-border innovation. As you probably do not know, De La Salle University was recognized by AUN SIDNet as lead institution in chemical engineering in 2001. One of the programs of the AUN SIDNet is collaborative research. This talk will highlight the different collaborative projects that I had in chemical engineering and have the characteristics of cross-border innovation that addresses the attainment of sustainable development goals. So the outline of my presentation will include the introduction about AUN SIDNet. Then I'll proceed to phase 1 collaborative research on methane reforming using steam. Then I will talk about phase 2 collaborative research on photocatalysis and proceed to phase 3 collaborative research on common regional concern. And lastly, I'll give you a summary and update on AUN SIDNet programs. This slide shows the different phases that have been involved in AUN SIDNet activities, which are phase 1 to phase 3, from 2003 to 2016. The ASEAN University Network, or AUN, was created in 1995 based on the initiative of the 4th meeting of ASEAN Heads of Government held in 1992, which emphasized the need to promote human resources development by considering ways to strengthen the existing network of leading universities in ASEAN region with a view to ultimately establishing an ASEAN university based on this expanded network. On the other hand, the concept of SIDNet evolved at the ASEAN-Japan Summit meeting held in December of 1997, when the then Prime Minister of Japan, Mr. Ryutaro Hashimoto, emphasized the importance of human resources development for sustainable economic development in ASEAN countries. Possible project ideas had been discussed since then and among the relevant authorities of ASEAN countries and Japan. The central issue became how to upgrade higher engineering education by way of creating engineering institutions network ASEAN-wide. Thus, the project on the development of Southeast Asia Engineering Education Development Network, or SIDNet, was proposed as a sub-network of AUN. The AUN SIDNet is established as a sub-network under the auspices of AUN and is composed of leading engineering institutions in ASEAN member countries, which is referred to as member institutions. The following are the objectives of AUN SIDNet. With a view to effectively utilizing regional available human resources for upgrading higher engineering education as a whole, the AUN SIDNET seeks to activate internationally competitive personnel in leading engineering educational institutions in the region, not only for advancing academic cooperation among themselves on equal footing, such as promotion of research activities and exchange of coursework programs, but also for providing educational and technical assistance to less advanced engineering institutions in the region where appropriate. Second, it is also anticipated that cross-border and region-wide development of engineering education and research capability would promote collaboration and solidarity between academics and professionals in the region, which will well correspond to AUN's founding principle. The AUN SIDNET is composed of a steering committee, member institutions, and a secretariat. De La Salle University is one of the member institutions. The member institution shall implement to the best of its ability the programs and activities of AUN SIDNET for which prior agreement has been reached. Furthermore, to ensure effective collaboration among member institutions, the members will endeavor to implement the following measures. So these are the functions of the member institution: to subsidize and tuition and other fees for selected disciplines, to authorize the secondment or exchange of faculty fellows to MIs where their services are required, to facilitate subsidy for accommodation for scholars and faculty fellows, to secure admission of scholars, to assist scholars to enable them to participate in on-the-job training in private firms, to facilitate exchange of library materials and publications electronically or through conventional means among MIs, to facilitate the cross-posting of researchers who are involved in joint research activities, to optimize the use of laboratory facilities in the region, to use its resources to complement AUN SIDNET Fund, to allocate from the budget of the university such amount as may be necessary to support priority program of the AUN SIDNET, to pursue support from the public and private sector for the AUN SIDNET programs, and to authorize eminent administrators or faculty members to serve in the AUN SIDNET Secretariat or the steering committee when nominated or selected. The member institutions come from Southeast Asia, which include Brunei Darussalam, Cambodia, Indonesia, Laos PDR, Malaysia, Myanmar, Philippines, Singapore, Thailand, and Vietnam. In the Philippines, there are 2 member institutions, and these are De La Salle University and the University of the Philippines. De La Salle University, as already mentioned, is identified as the host institution in chemical engineering. I was involved in different programs of AUN SIDNET from 2005 to 2015, which is from phase 1 to phase 3. The following activities that I have been involved are shown here: collaborative research, academic seminars, publications, presentation in international conference, graduate program for master's degree, short-term training, dispatch of Japanese professors, short-term study or PhD program in Japan or other ASEAN countries, including sandwich program, and other special projects like collaborative research with industry and collaborative research on common regional concern. This collaborative research, which is on methane reforming, was the first proposal submitted to AUN SIDNET for funding under phase 1 in 2003. Methane is the main composition of natural gas. Natural gas is abundant fossil fuel resource found all over the world. According to statistics, potential natural gas reserves in the Philippines is 3 to 4 trillion cubic feet. In Vietnam, 10 trillion cubic feet, and in Indonesia, 161.1 trillion cubic feet. It satisfies 25% of the energy demand in the country. But the main component of natural gas is methane, which is a greenhouse gas, causing climate change and global warming. One way to prevent greenhouse effect of natural gas is by utilizing it as an energy source. Natural gas, however, is situated in areas remote from the centers of highest energy consumption, and the cost of compression, transportation, and storage make methane an unattractive energy source. A large amount of research into the conversion of methane to liquids or higher hydrocarbons has been carried out. For example, the direct oxidative conversion of methane into methanol, formaldehyde, benzene, and other aromatics, and propanol have all been demonstrated. However, unfortunately, the yields achieved are too low or the processes are too costly. The other indirect conversion involves reforming natural gas into synthesis gas, or syngas in short, which is a mixture of carbon monoxide and hydrogen, and using this syngas to produce a series of important chemical products such as liquid fuel and methanol. Till now, the direct conversion has not found application in industry. At present, the application of natural gas in chemical industry is mainly by indirect conversion. So from natural gas to syngas is the first step. For this purpose, there are several choices. This includes steam reforming, partial oxidation, dry reforming, and autothermal reforming. Steam reforming of methane is a dominant commercial method suitable for hydrogen production and ammonia synthesis. The ratio of hydrogen to carbon monoxide in this case is rather high for methanol production and other products. So this process requires high operation temperature, leading to the activation of the catalyst and consume a large amount of energy. Many researches have been conducted related to this problem in order to reduce energy consumption and lowering of reaction temperature. The catalytic steam reforming of methane is a well-established process to converting natural gas into hydrogen or synthesis gas in industry. However, large amount of energy is necessary because SRM is highly endothermic reaction. The reaction is industrially operated at high temperature around 800 degrees centigrade over nickel alumina-based catalyst. Such high temperature causes some demerits, including the expensive tubular reformer made of high alloy nickel chromium steel, irreversible carbon formation in the reactor, and the large energy consumption. The lowering of temperature, however, may lead to lower conversion and increase in carbon deposition on the catalyst, thus causing the unwanted deactivation of the catalyst. The development of catalysts for steam reforming is based on the key problem to avoid the formation of carbon. In several years ago, this has been recent progress have been reported, resulting to better control of carbon limits and better catalysts. For nickel catalysts, carbon formation is avoided when the concentration of carbon dissolved in nickel crystal is smaller than at equilibrium. So, Rostrup-Nielsen in 2000 proposed the steady state carbon activity could be decreased by enhancing the absorption of steam, enhancing the rate of surface reaction, and also decreasing the rate and degree of methane activation and dissociation. Noble metal catalysts were suggested as an alternative solution because these metals do not dissolve carbon. It is known that carbon deposition is favored on catalysts with strong acidity and weak basicity. The previous study conducted by our scholar in the laboratory proved that nickel and zirconia had the highest basicity among the 4 catalysts used. These are nickel on alumina, nickel on silica, nickel on titania, and nickel on zircon dioxide or zirconia. This research was correlated to the activity test conducted by also our researcher, Mr. Monroy, in 2006. However, the best catalyst was not nickel on zirconia. The reason for this can be interpreted in terms of surface area. The zirconia used had the smallest surface area compared with the others. It is known that the catalytic activity has a linear relationship with surface area. Because of high operation temperature, the catalyst for steam reforming reaction has thermal resistance as well. The highest surface area may not be the highest, may not exhibit the highest catalytic activity. So, our study focused on the effect of surface area of zirconia on steam reforming of methane. In addition, modification of zirconia support by the addition of ceria led to the improvement of oxygen storage capacity and thermal resistance, as well as the promotion of metal dispersion on the support. The catalyst we developed was compared to a commercial catalyst used in Indonesia. It was proven to be better in terms of lowering the process temperature and preventing the activation due to carbon formation. The scholars and faculty members involved in this study are Hiroo Niyama from Tokyo Institute of Technology. He is our Japanese professor. And I, as the lead proponent from De La Salle University, and joined by Dr. Leonila Abella, also from De La Salle University, acted as advisor and co-advisor of our scholars. Anton Pornomo from Gadjah Mada University was our PhD scholar. We also have a faculty researcher from De La Salle University, Teddy Monroy. Another AUN SIDNET scholar is Miss Tu. She was our MS scholar from Ho Chi Minh University of Technology. And another trainee or fellow from Hanoi University of Technology visited our laboratory. He was Mr. Tui. So we can see pictures here of the different people involved in the study. Here is the list of our publication related to this study. We published them in reputable Scopus Index journals, and we presented them in what we call a conference, international conferences. So this is a picture of Anton in the Philippines with us as their advisors and Professor Niyama. You can see here also Anton presenting his paper. I accompanied him to the PICHE convention, the Philippine Institute of Chemical Engineers convention several years ago. And this is his picture when he graduated his PhD from De La Salle University together with our MS students from De La Salle University. And these are pictures taken in Japan, Tokyo Institute of Technology. This is Anton, and joined by some Filipino fellows working in Hinode Laboratory. And this is Anton with other international students at Hinode Laboratory. And this is now Anton, his recent photo. He is now the director of the Basel and Stockholm Convention Regional Center for Southeast Asia, based in Jakarta, in Indonesia. This center is supported by 10 countries: Brunei Darussalam, Cambodia, Laos, PDR, Malaysia, Myanmar, Indonesia, Singapore, Philippines, Thailand, and Vietnam. Since the ASEAN University Network, Southeast Asia Engineering Education Development Network, or AUN-SIDNET, was first established in 2001 through several joint academic and research activities in engineering field between ASEAN member countries and Japan, the project has made significant progress in human resources development in engineering. At the same time, through several joint activities such as collaborative research and regional conferences programs, the project has successfully established a strong network among researchers in ASEAN as well as ASEAN and Japan. And at the same time, linkage with industries or private sector was witnessed partly through local companies' participation in these two programs, although it was not in a very big scale or number. Meanwhile, the Japanese government approved additional funds to accurate overseas development of Japanese infrastructure, and the fund was allocated to AU and SIDNET to promote research activities in ASEAN countries. Therefore, aiming at further improvement of academic and research capability of member institutions with industrial linkage from Japan fiscal year 2011, the AU and SIDNET project has launched a new supporting program called Collaborative Research Program with Industry, or CRI, which covers AU and SIDNET's fundamental fields and both within ASEAN and with those in Japan, which will become a solid foundation for further research collaboration with industries. In this phase 2, which is from 2011 to 2013, another collaborative research proposal was submitted to AU and SIDNET. A semiconductor material. In photocatalysis, a semiconductor material such as titania oxidizes the organic contaminant in air or water with the use of ultraviolet light. It is known that photocatalytic degradation of variety of volatile organic compound, and it was demonstrated to be simple and efficient technique to purify polluted streams. Nevertheless, only some particular molecules with photochemical activity could be degraded through photolysis, and a large number of VOCs are still hard to process. It has been ultraviolet light is absorbed by the material. A semiconductor has a valence band and a conduction band. When UV light is absorbed by the material, the electrons from the conduction band travel freely to the valence band, forming electron holes. When this happens, band gap is formed. Band gap is formed, and the photocatalyst is activated. At the conduction band, electron hole reacts with water to form hydroxyl radical. At the same time, in the valence band, the free electrons react with oxygen to form superoxides. Both the hydroxyl radical and superoxides are capable of oxidizing organic pollutants. Titania absorbs UV light and breaks down the water into hydroxyl radical and also form hydrogen peroxide with oxygen from the air. Our work was focused on lowering the band gap, which is 3.2 electron volt energy, so that the photocatalyst will work with visible light coming from the sun. One way to lower the band gap is by adding a dopant. At the same time, recombination of the electron hole pair must be prevented. A new titanium has nanoporosity and more effective properties was explored, and this was synthesized using a modified sol gel method. The following research projects were completed, presented, and published under this project. And this project was participated by a Japanese professor from Tokyo Institute of Technology, Professor Hirofomi Hinode, myself as main proponent and co-proponent was Josephine Borja. Dr. Pailin from Burapa University acted as co-advisor from Burapa University. And we have 3 scholars here, AUN SIDNET scholar, Nguyen Trung Hieu, a PhD scholar from Hanoi University of Technology, Natawot Bunsa from Burapa University, he was our MS scholar, and Nat Min Doan as our MS scholar from Ho Chi Minh University. Photo shows the visit to printing industry in both Vietnam and Thailand. So the pictures above are pictures in Vietnam. We visited the printing company in Vietnam, and we also visited the printing company in Thailand, Sinakhon Printing City. So we introduced our photocatalysis technology to them for the modification of their wastewater treatment facility. Under phase 3, which is on collaborative research on common regional concern, our project was on the development of sustainable solution to coal ash management in Asian region. So one of the pressing problems of the coal-fired power plant is the disposal of coal ash, both fly ash and bottom ash. Actually, there are many ways to utilize them, but because of the amount of ash being generated in the power plants, not all of them are utilized effectively. So we actually propose in this project two ways. One is to use it as a secondary material to extract valuable trace metals from the ash using bioleaching and the production of engineering material called geopolymer from the coal ash. This project was headed by Dr. Michael Promentilla from De La Salle University and participated by 2 professors from Tokyo Institute of Technology, Professor Hirofumi Hinode and Professor Nakasaki. Dr. Gallardo, myself, and Dr. Florinda Bacani acted as co-advisor or proponents of the project from De La Salle University. We have 1 PhD scholar from Ho Chi Minh University, Nguyen Hoc Tang, and faculty researcher from De La Salle University, Martin Calao, and a PhD scholar from De La Salle University, Denbert Pangayaw. All of them graduated already with their doctoral degree from De La Salle University. And here are the list of our publications as well as technical reports presented in conferences. As a summary, AUN SIDNET has successfully implemented cross-border and international research collaboration through the exchange of research expertise in conferences, use of equipments, instruments, and laboratory facilities. The scholars also go back to their university, has widened their network through attendance in conferences and meeting of experts, and this means a multiplier effect. Then publication and presentation in conferences have made possible the transfer of knowledge and technology. We have to consider also patent disputes when we have implementing a cross-border innovation. Also, we found concerns on confidentiality agreement preventing us from publishing research results in the collaborative research with industry. And probably in the future, this could be explored, and that is the co-tutela or joint PhD by AUN SIDNET. A recent report shows phase 2 new programs and initiatives like the Alumni Support Program, attend regional conferences in different member institutions. And during the COVID-19 pandemic, they had a special research program for COVID-19, and the publication of the AUN SIDNET journal in engineering, which is called ASEAN Engineering Journal, which is already Scopus Index. Right now, it is already on the post-phase season, which started in 2023 and will end this 2026. And they are now eyeing the next phase to be in East Asia and Africa. Thank you very much for the opportunity to share. Here are my contact details. Thank you.
Thank you so much, Dr. Susan Gallardo. To show our appreciation, we would like to award this certificate of appreciation to Dr. Susan. Let me read first the content. Republic of the Philippines, Aurora State College of Technology, Barangay Zabali, Baler, Aurora, Philippines. This certificate of appreciation is given to Dr. Susan Manlastas Gallardo for your dedicated participation as guest speaker in the cross-border engineering innovation at Aurora State College of Technology, ASCOT Hostel, Barangay Zabali, Baler, Aurora, April 29, 2025, given this 29th day of April 2025. Signed, Engineer Alking B. Gorospe, the Director of our Research and Development Office. Signed, Vice President of Academic Affairs, Malus F. Cabatan. Signed, Renato G. Reyes, SUC President 2. Once again, thank you very much, Dr. Susan. Let's give her a round of applause. Thank you once again to all our brilliant speakers for generously sharing their expertise. Palakpakan po natin ang ating mga naging speakers.
And of course, to everyone who actively participated during the discussion, especially during the question and answer session, we truly appreciate your enthusiasm and of course, your engagement. Maraming salamat sa inyong lahat. Now to formally close today's international webinar on engineering, let us now hear or watch the closing remarks from the President of the JSPS Alumni Association of the Philippines, Dr. Karl Marx Quiazon.
Good afternoon, everyone. As we conclude today's Cross-Border Engineering Innovation webinar series, I would like to extend my deepest gratitude to all our distinguished speakers for sharing their cutting-edge research, experiences, and valuable insights. From groundbreaking work on composite material damage detection to smart agricultural machinery, AI-driven pavement engineering, advances in ultrasonic welding for electric vehicles, and spatiotemporal studies of urban heat islands, today's presentation have truly showcased the power of innovation without borders. We were also inspired by the latest development in magnetic refrigeration and material evaluation under hydrogen environments. Innovations in industrial HVAC system through CFD simulation, the perspective of young Filipino engineers forging paths across the globe, and the fruitful collaborative research and in chemical engineering made possible through AUN SIDNET. Today's discussion reminds us that engineering knows no geographical boundaries. It thrives on collaboration, diversity of ideas, and a shared vision for a better, more sustainable future. I hope each one of us leaves this event energized with new knowledge, new connections, and renewed passion for innovation that transcends borders. On behalf of the organizing committee, thank you all for being part of this journey. Let us continue to work together, inspire one another, and build a world where engineering innovation truly knows no limits. Mabuhay, and see you at our next event.
Thank you very much, Dr. Kiazon.
Before we end, may we request everyone to kindly turn on their cameras, especially our speakers. Dun sa mga nandun sa ating platform, may we turn on our cameras for photo opportunity to commemorate this successful event. So may I request the faculty and staff, so please come in front.
Dito na lang sa gilid. Okay. Okay, again, inviting all of the faculty, staff, guests, of course, here in front. Okay, let's allot a little space in the middle again, no? For the projection of the pictures of our participants and, of course, our speakers. Matatakpan sila, sir. Matatakpan. Tayo na lang ulit tayo sa gilid. Okay, so our participants online, please, you give your best smiles. Ano sir, pa-V po, pa-V. Again, please turn on your cameras. Okay. All right. Smile in 3, 2, 1. Again. Okay. Another. 1, 2, 3. Smile. Engineering as 1. And the ASCOT hand sign. All right, thank you very much. We would also like to inform that e-certificates will be given or will be sent to your registered email addresses within 3 days to 1 week. So you'll just have to wait for that because our committee will be working out on that. Please fill out the evaluation form because that would be the basis of our attendance. Okay? Also a requirement for the e-certificates.
Aurora State College of Technology, sa lalawigan ng Aurora, pagkasapan ng kabataan, pagkanapan ng bayan, ang tapat
ASCOT, hand sign. All right.
On behalf of the School of Engineering and Aurora State College of Technology, thank you very much for being part of today's international gathering of engineers and innovators.
Let us continue to break barriers and build bridges through cross-border engineering innovation. Have a great day ahead, everyone.
Mabuhay!